talk about dynamic type inference for gradual typing.
Okay, thank you for introduction. I'm Yusuke Miyazaki from Kyoto University. I present joint work with Taro Sekiyama and Atsushi Igarashi on dynamic type inference for gradual Hindley Milner timing. So let me introduce a background of our research first. Gradual typing is a framework to integrate static typing and dynamic typing in a single programming language. It introduces a dynamic type to specify dynamically typed parts in the program, and it combines the type checking at compile time and runtime. By using a gradually typed language, a programmer can evolve a fully dynamically typed code to a fully statically typed code gradually by adding type annotations little by little. So let me show an example. This is a gradually typed program which takes two arguments, x and y, and returns the average of them. This program is typed at int to start to int, and the str means a dynamic type. And the parameter x is annotated with int, and the parameter y is annotated with a dynamic type, which means that the value of any type can be passed to this parameter. In this program, whether x has int type or not is checked at compile time, but whether y has int type or not is checked at runtime. So let's apply this function to some different values. If we apply this function to integer values 3 and 5, obviously it returns integer value 4. If we apply this to string value and integer value, in this case, this program is rejected by compile time inference because the parameter x requires integer value. Finally, if we apply this function to an integer value 3 and the string value hello, then this program is accepted by compile time inference type checking because hello is a string value. But this is rejected by runtime type check because we cannot use a plus operator to a string value hello. Let me show another example. I'd like to show that a type annotation can affect the result of a variation in gradually typed language. So how this program is evaluated? First, identity function annotated with int is passed to the parameter f. Then an integer value 3 is passed to the parameter x, which is annotated with int. So this program is resulting in value 3 wrapped with cast. Cast may not be obvious, but we can ignore this for now. You can consider that this is some kind of value tagged with int. Then let's consider to change the type annotation for x to string instead of int. In this case, an integer value 3 is passed to the parameter x, which requires string. So runtime type error happens. In this paper, we propose the blame calculus to give a new semantics of the dynamically typed language with type inference and Hindley Milner polymorphism. We introduce a new idea called dynamic type inference to deal with the type variables left undecided by compile time inference. We prove various properties of the calculus, and we implemented the interpreter, and it's available as a reusable artifact on GitHub. So this is the outline of this talk. Let me explain the problem we are trying to solve in this paper first. I introduce the implicitly typed gradual language as a background, then proceed to the problem. So gradual typing has been applied to various language features. In one of them, there is an implicitly typed gradual language, ITGL. It is a gradually typed language with let-polymorphism, and it is equipped with compile time type inference algorithm. The key idea of the algorithm is that it only infers static types for where type annotations are omitted. A static type means that a type does not contain any dynamic type. Their idea enabled to return principal type. Okay, let me show how compile time type inference works in ITGL. This program is not has no type annotations. For this program, ITGL works similarly as ordinary statically typed language inference. So f is inferred as int to int, and x is inferred as int. And the result is obviously an integer value 3. So let's consider to add the dynamic type to the parameter f. In this case, ITGL cannot infer the type of x because by introducing the dynamic type, constraints are weakened. This can be the problem. Because if you are using ordinary statically typed language, you may be able to ignore type annotations at runtime. But as I said before, we cannot ignore type annotations in a gradually typed language. So let's consider to replace alpha with some concrete static type before evaluation. So actually, there are many candidates for alpha. But in this case, as you know, if we replace alpha with int before evaluation, this program successfully results in a value. But if we choose other type, it results in runtime type error. Actually, we want to result the second program in a value because this program is obtained by one dynamic type to the first example. But generally, it is difficult to find a static type for alpha at compile time. So this is our solution. Basically, our solution tries to find static types for undecided type variables during evaluation. It means that in this example, our runtime type system will find out this alpha should be int. Another idea to tackle this problem is that replacing all undecided type variables with the dynamic type. Yeah, it's simple, and it may sound like a good idea, but we find some problems. One is that it goes against with the original idea of ITGL, that a type variable is a placeholder for a static type. A second problem is that it makes it difficult to detect a type error earlier because it can make evaluation successful even when there is no static type substitution that can make evaluation successful. That's why we decided not to take this approach. Next, I explain about dynamic type inference. To discuss it formally, let me introduce cast used for runtime type check first. Then I will explain dynamic type inference. So cast is a special term for performing runtime type check in blame calculi, and it is written like this. This cast basically checks a term which has type of u can be used as u prime or not. If this cast fails, it is expressed using a special term called blame. Actually, we deal with the blame levels in the paper, but we omit blame levels in this slide for simplicity. And usually, gradually typed language semantics is given through translation into a blame calculus. And casts are inserted during that translation to where runtime type checks are required. So let me show how cast works using example. So this example in the gradually typed language is translated into a blame calculus like this. It inserts a cast for x from star to int and cast for 3 from int to star. Now, this part is already a value tagged with integer. So we use beta reduction now. So this program evaluates to this term. And this part is actually an abbreviation of two sequences of casts from int to star and from star to int. Blame calculus conducts runtime type check here. And obviously, cast from int to int succeeds. So this program successfully evaluates the value 5. Let's consider to apply the same function to a string value hello. First two steps are the same. But here, runtime type check fails because cast from string to integer is not possible. So this program results in blame, which means runtime type error. Let me explain another example. By inserting cast, we obtain the program like this. Cast for 3 and identity function will be OK, but the cast for f may not be obvious of some of you. Actually, it only checks f can be used as a function type or not, but we cannot check the source type and target type for now. After a few steps of evaluation, we obtain the term like this. Then we conduct runtime type check as usual. Then this program evaluates to a value. OK, let me explain dynamic type inference using the similar example. The only difference is the type annotation for the parameter x. As I said before, the first steps are the same. And here, we use dynamic type inference. Our dynamically type inference instantiates this alpha type variable with the type attached to a value, in this case int, and proceeds the evaluation. So dynamic type inference generates type substitution, which replaces alpha with int, and all alpha in the program is instantiated. Then we can successfully evaluate this program to a value thanks to dynamic type inference. Next, let's formalize the idea of dynamic type inference. Our calculus is basically simply type blame calculus extended with type variables and let-polymorphism. Actually, extension to let-polymorphism is not on this slide. It's discussed in the paper. And the types of our calculus includes the dynamic type, type variable, base type, and function type. And terms of our calculus includes the terms of simply typed lambda calculus and terms used for blame calculus, cast and blame. Next, we extend reduction rules for dynamic type inference. Our reduction rule is written like this. It means that our term E is reduced to E prime, and DTI generates the type substitution S. The first rule instantiates a type variable with the base type. It generates a type substitution, and then cast succeeds. The second rule instantiates a type variable with a function type. But actually, we don't know the source type and target type for this function now. So we generate new two flash type variables. Then we instantiate alpha with a function type with two new flash type variables. We also modify the evaluation rule for dynamic type inference. Our evaluation rule is written like this. And when a subterm E is reduced to E prime using the DTI, then we apply the type substitution obtained by DTI to the entire term. This modification ensures that one type variable in the program is instantiated at most once. As you can see in the example, all alpha in the program is instantiated with int after one step of evaluation. Now, we explained the formulation of calculus. So let me explain the properties of our calculus. We have proved various properties, including type safety and soundness and completeness of DTI, and gradual guarantee of our calculus and ITGL. We focus on soundness and completeness of DTI in this talk. Soundness and completeness of DTI basically means that DTI always returns an appropriate type substitution if it exists. An appropriate type substitution means that by applying it before evaluation, the program successfully terminates at the value. In other words, DTI tries to avoid to be blamed as much as possible. These ideas correspond to soundness and completeness of ordinary static type inference, but the statements differ. A soundness of DTI says that a type substitution yielded by DTI is appropriate, and completeness of DTI states that if an appropriate type substitution exists, DTI returns one. This is a formal statement of the first item of the soundness. I'll explain the intuition of this property. It means that if a program E results in a value of blame R with DTI, then applying substitution obtained by DTI beforehand doesn't change the result. The second item of soundness says that if a program E evaluates the blame using DTI, applying any type substitution results in blame. This is the completeness of DTI. The first item says that if we're type substitution S that can make a program result in a value, then a variation using DTI also results in a related value. The second item is simple. It says if there is type substitution that can make a program diverge, a variation using DTI also diverges. Let me conclude this talk. In the paper, we provide full definition of our calculus, and we show extension to let-polymorphism. Our semantics of let-polymorphism is not parametric, actually. And our let-polymorphism semantics behaves like this. A program with let and program obtained by expanding let results in the same. We also show the properties of calculus. Actually, our gradual guarantee of our calculus and ITGL requires non-trivial precision relation. As a related work, there are some work about which suggests to replace undecided type variables with dynamic type. As I said before, the work provides more permissive semantics, but our approach provides more earlier bug detection, and the approach is also consistent with the original idea of ITGL. So in the paper, we presented the blame calculus with dynamic type inference and let-polymorphism. We introduced a dynamic type inference, which instantiates undecided type variables along with evaluation. Thank you for listening.
The microphone goes. So let me ask, what about mutability and value restriction?
OK. First, our semantics of let-polymorphism uses value restriction. And what mutability means?
So if you extend your core language with mutation, would this work?
Like difference? Actually, we didn't consider it yet.
So if you change the evaluation rules, it seems that it is different from your group's previous work, system FG, FC. Then usually in static type functional languages, we can use system F as a core language. Here, then it means that they're just different right now?
Yeah, I think, yeah, it's a good question. Actually, we didn't use the polymorphic blame calculus as a to implement let-polymorphism. Our approach is somewhat more naive. We basically use simple substitution to implement let.
Hi. You mentioned that other work had looked at replacing the type variables with the dynamic type, and that instead you're using these dynamic type inference. Did you consider doing the dual, which is replacing all of the dynamic types with dynamic type inference? What happens if you make the whole language dynamic type inference? Not the static types, but get rid of the stars and make them alphas.
Yeah, it's an interesting suggestion. But yeah, actually, there is a program that cannot be written only using a type variable approach, because by using the dynamic type, we can write program more flexible.
Let me ask, can you say a bit more about why the precision relation is not trivial?
Yes, so our precision relation is extended to implicitly typed language, so which means that sometimes there is no type annotation in a term. We define the term precision relation to cover that term.
Let's take the last one as the next speakers.
So there are two results I would have expected to see that I didn't see mentioned, one you alluded to. So one is that you preserve parametricity, and you said we don't. So there the question would be, could you, or is that hopeless? And the other is you're working with blame calculus, but I didn't see a blame theorem of any kind.
Actually, we didn't try hard to enforce parametricity in our calculus, but yeah, I think it's not easy. And I like the idea of parametricity, but in this research, I took what's intuitive or natural for programmers writing programs, like binding let should not change the result or not.
Okay.
What about blame? What about actually having a blame result?
We didn't state anything about blame theorem, actually.
Hint, the name's in the calculus.
And with this, let's thank the speaker again.